Hi folks, this video is going to be on the type of features that are formed by intrusive volcanic, extrusive volcanic and seismic activity. So, having gone on from geological theory and on from magma types, if you haven't watched those videos yet, you need to watch those before you watch this video. We've gone through those, we can now start looking at the types of landforms, and we're going to start with intrusive volcanic. Now they're called intrusive because they're inside the ground, or at least they were inside the ground when they were formed. So an intrusive feature is one that was formed in the ground and then came about on the surface later through the processes that I will explain. Another term that's used for them is relic landscapes, because they were formed ages ago. They are sort of relics from another time. So let's have a look at what happens. On this diagram we've got the mantle here, we've got the Moho, which is mentioned in the other video, at this point between mantle and asthenosphere. Above asthenosphere we've got a Sima, ocean plate, and a Sial, continental plate. Now, an intrusive feature forms basically when magma cannot reach the surface. It rises up from the mantle for some reason, and then it cannot reach the surface to form a volcano. Now this could be just because of a hot plume inside the mantle, a hot spot type affair. So you have hot mantle coming up, cuts through and rises up into the continental crust. Or it can be caused by the melting of a Sima oceanic plate. Now, what happens here is that rather than having a stream of magma coming up, you've got a blob of magma. Hence why I've given dashed lines rather than solid lines. Dashed lines because it's a blob of magma that's making its way up through the rock. Now this magma begins to make its way through, but as it rises up, it begins to cool. So it's rising up, it's cooling, it's picking up silica impurities from the continental rock. So it's becoming thicker and it's becoming cooler. Now, as this magma rises, it will leave behind any of its Sima constituents down towards the bottom. So the Sima parts get left behind, and it's only the Sial that rises up. The reason for this is because Sial is less dense, so it rises quicker. But it's a double-edged sword, because less dense things, while they'll rise quicker and leave behind that dense Sima, something that's less dense won't hold its heat as well. So as it becomes less dense, it'll cool quicker. And eventually it gets to the stage where it's picked up so many impurities and it's cooled that much that it comes to a stop. And this blob of magma holds fast in the surrounding rock, otherwise known as country rock. So that's could form here, or it could form from a subduction zone. So it could form from a hot spot many years ago, or a subduction zone many years ago. Either way, same process happens. The magnesium parts get left behind. It's only the Sial that rises up. If it cools too quickly to reach the surface, it stays in the middle. Now that blob, from the point it rises to the point it cools, is called a pluton. And once that magma is cooled, it goes from being called a pluton to being, well, whatever it is that we then see. and it becomes an intrusive landform. So, to recap, hot magma comes up from the mantle or from a subduction zone. It leaves behind the cyma, because it'll be a mixture of cyma and sial. Leaves behind the cyma, only the sial rises, but it cools too quickly to reach the surface, because the sial is less dense. So it rises fast, but it cools quickly. Gets stuck, and then it sticks fast. So far, so good. Let's take a look at a larger scale diagram. We've got our mantle, and we've got our Pluton working its way up from the Moho, the joint between the asthenosphere and the mantle, rises up through the asthenosphere into the country rock. It's cooling, eventually it forms our Pluton here, which cools. Now what we've got in the country rock is several layers. Now these are sedimentary layers generally, or they could be igneous, they could be metamorphic, but there are several types of rock. And they formed in layers many, many years ago, which means there are joints between them. So there are cracks between the rocks, but also because the Earth has cooled and warmed many times over ice ages and then interglacial periods, the surface and the joints between the rocks have also cracked vertically over time. Because it's expanded, it's contracted, expanded, contracted, eventually it develops cracks. Like anything that expands and contracts many, many times. If you think of, say, an ice cube that's then put into hot water very quickly, it cracks. Same principle here. What it means is that there are several cracks all the way through the country rock. And as the Pluton, which is hot magma, it's basically like hot metal. It's the same kind of consistency. As that rises and cools, it fills these cracks along here. There we go, that's the magma filling in the cracks there. And the rest of the Pluton is there. And of course it fills in these cracks down here as well, but they're less important for our purposes. As time passes by, and the surface of the rock has been eroded away, which leaves us with these features on the surface. They were underground, but now they are on the surface. We have got a batholith, hundreds of kilometres in size, or the slightly smaller laccolith. That's this raised part here. We might have get it right. We might have a dike and a sill system as well. Sills, like a windowsill, go horizontally. Dikes go vertically. Now it's unusual for them to stand up like that, they tend to be eroded down, but this is just to prove a point really. But they go vertically, sills horizontally, batholiths and laccoliths large areas. Now this is formed from Sial, remember, because Sima was left behind towards the bottom. As it's Sial, it means that this is a relatively low density magma that's risen up. And that means we get relatively low density rocks. We get rocks such as granite. Now you may not think that granite is a low density rock, it feels pretty solid, but actually as igneous rocks go, it is, relatively speaking, a less dense rock, especially compared to Saima rocks, thinking more like basalt. As well as granite, well, there's a whole range of different rocks, and I'm going to send you a resource that will give you some idea about the types of rocks, but granite is the classic case, particularly around the Isle of Arran, Dartmoor, which is a batholith as well. These tend to be the bases of our intrusive features. So where they've come from in terms of plate boundaries, well, they tend to be near to convergent boundaries. Well, ex-convergent boundaries a long time ago. It's very difficult to tell whether they were, but we assume that they could be from convergent boundaries, or they can come from hotspots. They don't tend to happen at divergent boundaries because the magma is basaltic and basically will just burn straight through and form an extrusive feature. Hasn't got that distance to go through. Doesn't tend to happen at transform boundaries because there's less volcanic activity at transform boundaries. So those are the intrusive features. Next we will look at the extrusive features.